Hello everyone. It is now time to go beyond the realm of approximations for definite integrals to define and compute the exact value of definite integrals using the limit definition of definite integrals. So here we go. So 2 points that are absolutely crucial before we go and we define and compute exact values of definite integrals about Riemann sums. So first, a Riemann sum is just a sum of areas of rectangles. Well, it's sine areas because if the height are below the x-axis, we consider these areas to be negative. So in other words, we're using basic geometry to compute a Riemann sum. Again, Riemann sum sounds fancy, but it's just a bunch of areas of rectangles. And the second point, the important point, is that we're using these rectangles to cover these fancy regions under functions. So these Riemann sum are used to approximate definite integrals for function f over intervals a, b. So we only have ways to approximate these definite integrals. But now the goal of this section is to find a way to define the exact value of a definite integral and then, of course, compute it. The limit definition of definite integrals comes from a very interesting observation. What happens if you are looking at a Riemann sum and you are increasing the number of rectangles used to approximate your definite integral? And with that observation will naturally come the actual limit definition of the definite integral. So what I've done for you is I'm going to look at the function 0.5x cubed minus x squared plus 2 over the interval minus 0.5 and 2, and we're going to compute a bunch of Riemann sum. Actually, we're going to use a midpoint sum. We're going to look at the Riemann sum when we use 2 rectangles, 5 rectangles, 10 rectangles, and 20 rectangles, and see what happens visually. And this visual observation should seed in your mind the actual limit definition of the definite integral. So first, I've done the midpoint sum using n equal 2. If you do the actual computation, this is a good exercise, of course, you're going to get 4.24316. And as you can see, these 2 rectangles are doing a nice job to cover the definite integral, so the gray zone of f of x over the interval minus 0.5 to 2. But of course, the first rectangle is overdoing it, but the second one is not doing it as well. But this is what you get when you're using 2 rectangles using the midpoint rule or the midpoint Riemann sum to cover this region. Now, if you do the exact same thing, but now using 5 rectangles, this is actually an example we looked at earlier in the previous section. So if you compute me5, you're going to get 4.27734. And now you can see that these 5 rectangles are doing, like in red here, are doing a better job to cover the gray zone for the function over that interval. But if we continue this process, so for example, now let's look at what happens if we cover this region with 10 rectangles. So if you do the actual computation, this is actually very tedious, but if you do it as an exercise, you can double check that the me10 is 4.282222, etc. So now visually we can see that these 10 red rectangles are doing a pretty good job covering this gray zone. And again, if we push this a little bit more, let's say we are now computing me20. So if you're using me20, sorry. Oh, this is like a bilingual, like Riemann something, sorry. So if you're computing me20, so if you're using 20 rectangles, you're going to get 4.28344. And as you can see, this is so beautiful to look at. Like when you look at these 20 rectangles, and here take the time to really appreciate like how these rectangles are constructed. So I took the interval from minus 0.5 and 20. I've divided this interval into 20 sub-intervals. I used the midpoint of every single interval, sub-interval, and I've computed the output of the function, and I used that output, the y value, as the height of the rectangle. So this is really a very nice visual representation of the midpoint rule for 20 rectangles, and you can see that these rectangles are really doing a good job. So they are covering the region, the gray region, the definite integral, the thing that we're trying to define and compute exactly. So the more rectangles you use, it seems that the better this approximation will be. So we can summarize this observation as following. So I'm going to read it out so that it's said properly. So when n increases, which means like when you're using more rectangles, then the Riemann sum using these n rectangles seems to be getting closer to the definite integral of the function f of x over the interval ab. So when these approximations are going to get closer and closer to a number. So if you're using more and more rectangles and you're computing these approximations, so this will give you a sequence of numbers. When these numbers are getting closer to something, so it's like you're guessing a limit using a table, we're going to write this as follows. So when n gets larger, so we're going to write as n goes to infinity. So of course, remember when you say n goes to infinity, it simply means n is getting bigger and bigger. You never reach infinity. So you're just pushing it with larger and larger numbers for n. Then these Riemann sums. So the more rectangles you use, the better these approximation will be. So this is what this notation is telling you. Again here, I really want to stress the fact that you need to really feel it in your belly. Okay, so the more rectangles you have, the better your approximations are. And yes, we can use that notation to illustrate that, but the notation here is used to reflect on something you understand first. You're not trying to understand what a Riemann sum is and what it does. Looking at these arrows and these symbols, you need to see it first. Oh yeah, the more rectangles I use, the better these approximations are. And the corresponding notation is n arrow to infinity, means that rien, Riemann sum with n subrectangles, n rectangles, gets closer to the definite integral that we're trying to define and compute. All right, got very emotional there, but the more rectangles you use, the better these approximations will be, the closer you get to your target. But now, how do we get there? How do we get there? Well, by actually using the definition. Here is the limit definition of the definite integral. So just a friendly warning, the actual definition here should be very intuitive. The more rectangles you use, the better your approximation seems to be. So if you just push this to infinity using a limit, you should get an exact value that will be used to define and compute the definite integral. But in practice, this very nice definition is almost impossible to use. Okay, so we'll have to find like tricks to get to the exact value using this definition, but using shortcuts to this definition. But one thing at a time, first and foremost, here's the definition. If you start with a function f over the interval ab, we will say that the function is integrable over ab. It's actually Riemann integrable because we're using Riemann sum. There's other ways to define integrable. But anyway, so we say that f of x is integrable over the interval ab if, when you're pushing n to infinity, so if you compute the limit as n goes to infinity of any Riemann sum, if this limit always exists, and if this limit is always the same, then we say that this function f of x is integrable over the interval ab. And in that case, if for every single Riemann sum out there, left, right, midpoint, 2/3, 1/3, whatever you want, and of course there's infinite amount of Riemann sums, if you always get the same value for these limits, we will say that the actual value of the definite integral, so the integral between a and b of f of x dx, is equal to the limit as n goes to infinity of those Riemann sums. All right, so that's the definition. You're using Riemann sums, you're letting n go to infinity. For any Riemann sum, it always gives you the same number. That's going to be the value of the definite integral for the function f of x over the interval ab. But here's a bunch of remarks. So in this chapter, Okay, we only use regular Riemann sums. So what that means is that the delta x, so when I say use n rectangles, you just take your interval AB and you split it into n pieces where all these pieces are the same length. But you can actually consider a Riemann sum where you divide it into n pieces where the pieces could be anything. Okay, so, but what's really important though is when you're using more and more rectangles, the width of those rectangles, they need to get to 0. So they need to get smaller and smaller. Okay, you don't want just to divide a portion of the integral of the interval. Anyways, so for that definition though, you need to look at every single type of Riemann sum where the subintervals, the length of the subintervals are going to 0. So this is just saying that there's a lot of them. Okay, so it's a lot of work to actually compute the limit definition of a definite integral. But it's the definition. Okay, so that's the way it works. Like if you have a function and you slice it any way you want, the more rectangles you use, you're always getting to the same number. That means the function is integrable. So that's the definition. It's very nice. Like it's supposed to be very intuitive. More rectangles you use, the closer you get to your value. So if you push this to infinity, and the only way you can push something to infinity in calculus is by using a famous limit. So when you compute the limit as n goes to infinity of a Riemann sum, of any Riemann sum, you always get the same number. That's the definition of the definite integral of the function f of x over ab. So it's magical. Okay, it's powerful, but nice definition, but terrible to compute. Like, how are you going to compute such a thing? Like, you cannot compute the limit as n goes to infinity of every single Riemann sum out there. There's infinity amount of them. So it's impossible to use. So again, this is like what's really interesting with this definition is it's very intuitive. You get it. You know what you want to do, but it's very difficult to do. But thankfully for us, there's a nice trick. And the next theorem will be that trick that will allow us for nice functions, which are going to be the case in this chapter, to compute the limit definition of definite integrals, but using only one Riemann sum. Okay, so going to infinity. And then for that one, whatever number you're going to get will be the actual number that you're looking for. So merci, prochain théorème, merci. All right, so here it is. The right theorem. The right theorem is actually something very simple to state, and it goes as follows. All continuous functions over the interval AB are integrable, period. That's it, that's out. Okay, so that's the idea. This might sound like nothing initially. Okay, all continuous functions are integrable, so what? Well, by definition, a function is integrable if the limit as n goes to infinity of all Riemann sums, they always go to the same number. That's a big job, okay, computing the limit for all Riemann sum. And we're a lazy piece of shit. We don't want to compute the limit of all Riemann sums. But if you know your function is continuous, by this theorem, you know it's integrable. So this means if you compute the limit of one Riemann sum, for example, the right Riemann sum, this is why this is called also the right theorem, then whatever number you're going to get, if that limit exists, is the actual value of the limit definition of the definite integral. So you just have to do it for one. So this theorem is really, really fun because if you compute the limit of the right Riemann sum, if that number exists, then it needs to be, since all of them are the same, if you find one of them, well, it's the actual value that you're looking for. So this theorem simplifies our computation. It's not going to make it easy, by the way, but it does simplify our task because you just have to do it for one Riemann sum. And of course, in this chapter, all our functions are going to be continuous. So all our functions are going to be integrable. So you just need to set up a right Riemann sum and study its behavior as n goes to infinity to compute the value of the definite integral for that function. So very, very powerful theorem that simply says you can look now just at right Riemann sum and check what happens when n goes to infinity. If you find that value, it's the value that you're looking for. So super cool stuff, super cool stuff. So here is how I'm going to set up and compute the definite integral of a continuous function f of x over interval ab using the right theorem. The first thing you do, Step 1 is just to compute delta x, which is the width of all the rectangles you're going to use. So just here, a lot of notation, but basically what you're trying to do is set up a right Riemann sum, but using n rectangles in general. Instead of doing it for 4 or 5, like we did it before with a specific number, you need to do it in general for n rectangles, because now we want to understand and study what happens when this n value, when the number of rectangles gets bigger and bigger. So first you compute the width of those n rectangles. So delta x will always be b minus a divided by n. Then for all those subintervals, we're going to compute the endpoint of those subintervals, because we're going to use the right Riemann sum. We're going to need the right endpoint of those subintervals. So here the xk's, so the endpoints of your subintervals, are going to be a plus k delta x. So you're just making little steps of delta x. So x1 is just a plus delta x, x2 is just a plus 2 times delta x, etc. until the last endpoint xn, which is a plus n times delta x, which simplifies actually to b. Then, if you want to compute a Riemann sum, you need the base. Of course, the bases are delta x, but what about the height? So the height are just the values of the function at the right endpoint. So f of xk will be is the height of the kth rectangle from the first one to the last one. And then what you do is you compute the sum of the areas of all those rectangles from 1 to n. And this is where it's going to be algebraically intense. You want to simplify Rn as much as possible. You want to simplify the right Riemann sum using n rectangles so that you get a formula that only depends on n. And once you have that formula that only depends on n, you're going to study its behavior by finally computing its limit when n goes to infinity. And if you get a number, that's going to be the exact value of the definite integral for your function f of x over the interval ab. In order to simplify step 4 is always the trickiest one when you're trying to compute the exact value of the definite integral using the limit definition. So step 4 is the trickier one. So the next theorem is just a bunch of algebraic tricks that you can use in order to get rid of large sums by replacing them with nice little formulas. This is what I call, or I will refer to as, the Star Theorem. So the first point of the Star Theorem is if you add the first integer, if you go 1 plus 2 plus 3 plus etc. all the way up plus n, so if you're summing all k's from 1 to n, so here the sigma notation is just a compact form to represent the summation here. So you're summing all numbers from k equal 1 to n. Well, there's a formula for it. You just go n times n plus 1 over 2. This is actually a formula that Euler came with. So if you could just go n squared plus n divided by 2. So if you want to add all numbers from 1 to 1 million, you just go 1 million squared plus 1 million divided by 2. And that will do the trick. So it's a very nice shortcut formula. The sum of the first n squares, so suppose you want to add all integers squared, like for example 1 plus 4 plus 9 plus 16, all the way up to n squared. Well, so if you're summing all k squared from 1 to n, then there's a formula for it. So it's n times n plus 1 times 2n plus 1 divided by 6. Sometimes we prefer to use, and this is what I'll do most of the time in my examples, use the FOILed version. So 2n cubed plus 3n squared plus n divided by 6. Another formula that we will use in our examples, the sum of the first n cubed. So if you want to add 1 plus 8 plus 27 plus etc. all the way up to n cubed. So if you're summing all k cubes from the first one to the nth one, well, it's n squared times n plus 1, all that squared, divided by 4. If you FOIL it, that's the same thing as n4 plus 2n cubed plus n squared divided by 4. So if you want to add again here, maybe you need to do a couple of examples with actual numbers. If you want to add like 1 to the power 3 plus 2 to the power 3 plus 3 to the power 3, let's say all the way up to 10 to the power 3. You could do it using brute force by adding all those numbers together, or just by plugging 10 in that formula. If you go n to the power 4, 10 to the power 4 plus 2 times 10 to the power 3 plus 10 to the power 2 divided by 4, this will give you that summation very quickly. So it does not matter how big n is, these formulas, they give you those summation very quickly. So they're they're explicit formula that gives you these large sums. So it does not matter if n is 5, 1,000, or 1,000,000,000, it's the same formula. So very nice formulas that simplifies greatly some of those computation, because here, keep in mind what we're trying to do here. We're trying to add, areas of rectangles, and we want to have like a lot of rectangles, so n of them, where n gets bigger and bigger. So already, if you've done examples where you computed Riemann sums, already with 4 or 5, it's annoying, or with 8 or 10, 20, it's really annoying. So you don't want to add like large numbers. You want to find a way to compute this explicitly very quickly, and the Star Theorem will be very useful for that. Here we go. Let's compute the integral between 0 4 of x squared dx. So the first thing to notice here is that the function x squared, which is a polynomial of degree 2, is always continuous over its domain, which is R. So in particular, boom, okay, x squared is continuous over 0 4. This is very important because this gives us the green light on using the right theorem. So we're just going to compute the limit of the right Riemann sums because the function is continuous. So it really simplifies our question. So the first thing I like to do once I know that my function is continuous is to label the endpoint. So it starts at 0 and it ends at 4. So boom, the a value is 0 and the b value is 4 in my formulas. Now I'm ready to use the 5 steps to compute the limit definition of the definite integral. Step 1 is computing delta x. Delta x, which is b minus a over n. So in this question, here we go, boom. So delta x is going to be 4 minus 0 over n, which simplifies to 4 over n. So the width of every rectangles, when I'm using n of them, is 4 over n. So if you're dividing your interval, which is 4 long, into n pieces, the subintervals, the length of those subintervals are going to be 4 over n. Step 2 is to compute the right endpoints of those subintervals. So the formula is always xk is equal to a plus k times delta x. We have a, it's 0 in this case. We now have delta x freshly computed to be 4 over n. So you just plug everything. And the k stays k in this question because we have k subintervals from the first one to the last one. So boom. Okay, so here xk is 0 plus k times 4 over n. So 4 over n here freshly computed by delta x, which simplifies to 4k over n. So the kth right endpoint of the kth subinterval is going to be given by 4k over n, where k goes from 1 to n. So we have k. K here is just an index that labels all the rectangles from the first one to the last one. Step 3 is to compute the height of the kth rectangle by computing the output of the function at the rightmost point of your kth subinterval. So step 3 is to compute f at xk. So in this case, boom, f of xk. So here xk freshly computed to be 4k over n. When you square it, because here the function is very simple, it's just x squared. So xk squared is 4k over n in a bracket to the power 2. So you get 16k squared over n squared. So always take the time to simplify it as much as possible because we're going to be using that formula for xk. So xk is 16k squared over n squared. Again here, what xk computes, it's the height of the kth rectangle from the first one to the last one. Now the big step 4, the computation of the right Riemann sum using n rectangles. So again here, it is a bit stressful because you are computing the area of n rectangles where n can be anything. but it's important to keep n general because we want to push that n to infinity. So here we go. So Rn is always the sum of all rectangles from the first one to the last one. So sigma from k equal 1 to n of f of xk, so the height of the kth rectangle, times delta x, which is the width of every single rectangle. So here we go. Boom. So that's always the first line of the computation. Rn is the sum of f of xk, which is in our case 16k squared over n squared, times delta x, which is in our case 4n. And then the next thing to do is to simplify this as much as possible. In this question, it's not too bad. We only have one term. So we can actually just algebraically play with that equation. And here when you're playing with summation, so the sigma notation, anything that does not depend on k, because k is the only thing changing in these summation, you can factor this out outside of your sigma. So here the 16, the 4, the over n squared, and the over n, all of those are just coefficients that are not changing. You can factor this outside of your summation, and then this simplifies to the following equation. So if you take 16 times 4 outside, you're going to get 64. If you get n squared and n at the denominator outside, you're going to get over n cube, and the only thing that depends on k is k squared. That is stuck, that is changing, so this needs to stay inside your summation. So here we go. This simplifies to 64 over n cube over the summation of k squared from k equal 1 to n. In every single question about Riemann sum, you will always end up with a bunch of summation. Either you're going to sum up the constant 1, you're going to sum k from 1 to n, k squared from 1 to n, or k cube. And this is where you're going to use your star formula. So we know by the star theorem that the summation of k squared is given by n times n plus 1 times 2n plus 1 over 6. So you use the star theorem. You don't want to keep any sigma. So the goal here is to really get rid of the sigmas. So here, sum of k squared is just n times n plus 1 times 2n plus 1 over 6. Once you don't have any sigmas anymore, so what this formula is, so just take a moment to appreciate the power of this formula. What this formula is telling you, so if for some reason I want to approximate the definite integral of x squared between 0 and 4 using, let's say, 1,000 rectangles using the right Riemann sum, you could, if you know nothing, just take the interval, divide it into 1,000 pieces, and then just compute the width of those subrectangles, which would be 4 dividing by 1,000. Then you would need to evaluate the function 1,000 times for all those subrectangles, and then it's no, you don't want to do this. Or you can just plug 1,000 in this formula. 64 over 1,000 cubed times 1,000 times 1,000 plus 1 times 2,000 plus 1 over 6. This will give you the exact same thing. So it's an explicit formula. If you want to have 1,000 rectangles, 1,000,000 rectangles, nice. Okay, I can just do it in one shot thanks to this formula. Once you have your explicit formula for Rn, so a formula that only depends on n, you want to study what happens when n gets larger and larger, because this is actually the limit definition of the definite integral. So here's step 5, boom. So step 5 is, well, the definite integral of x squared between 0 and 4 dx, or the integral between 0 and 4 of x squared dx, is the limit of Rn, where our Rn here is explicitly known. Now we have a formula, 64 over n cubed times n plus 1 times 2n plus 1 over 6. And now what you have to do is simplify this a little bit. So here, if you just use a foiled expansion of your numerator, this simplifies algebraically to 64, open a bracket, 2n cubed plus 3n squared plus n, and the 6 times n cubed is now 6n cubed. And when you're computing, and this is something you can do in these computations, when you're computing limit, because you're always going to get this type of equation, when you're computing limits going to infinity of rational expression, you can just keep the highest degree terms. So you can just keep the highest degree terms here. La 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 la. So this equation would simplify as the, boom, limit of as n goes to infinity of 64 times 2n cubed. So you're just keeping the 2n cubed. So this simplifies to 128n cubed over 6n cubed. There's only one term at the denominator. And now this is where the magic happens. And if things are done correctly, this will always happen. So if you cancel the n cubes, 128 over 6, that simplifies to 64 over 3. So this is the value of the region under x squared over the interval 0, 4. Remember, this was our example, easy to illustrate, where we realized very quickly that we could not use basic geometry to compute that area. So we had to first guess it or approximate it using rectangles or Riemann sums. But now we have the exact value. That region, that pink region from that previous example, is 64 over 3. Nice. Very nice. All right. For that very short video, that's it. That's all. Bye-bye.